Hi, I am Lavanya, the founder of MachineLearningInterview.com, which is a platform to help prepare for machine learning interviews. So today we are going to do a code along session on automatic question answering from FAQs using BERT Embeddings. So a little bit about myself before we get started. I did a PhD in machine learning from the Indian Institute of Science, and I've been in the industry for over 10 years, starting with Amazon in Seattle and then Amazon in India and several companies in India like InMobi and Myntra and so on. So without much further ado, let's get started with today's code along session. So the code for today's session is all available on GitHub and you will be able to access it, and I will be using a Python notebook. But before we jump into this, let us actually look at the problem that we are trying to solve today and get a little more understanding of that, right? Okay, so suppose a user comes to my website. Let's take the example of my website, MachineLearningInterview.com, right? A user comes to the website and wants to know, do I need math to become an ML engineer? And this is a very common question, right? And the website already has a whole bunch of FAQs that contain information, including, something relevant for this question. So let's look at the website actually. So this is my website. Let's go to the FAQ page. And you can see like a whole bunch of FAQs. Any insights on the job market? What is the impact of COVID on data science roles? And so on, so forth, so on, so forth. Do I need to prepare algorithms and data structures for data science interview? And yeah, what is the mathematical background required for a data scientist, right? So this is not the exact same thing that the user asked, but it is close enough. If I get an answer to this question, it is relevant for the user, right? So what we want to do here is look at a user query and find the closest FAQ question to the user query. So the user query is a sentence and this FAQ question is a sentence. The problem really is find the closest, we need a way to find if two sentences are close to each other. That way we can find the closest FAQ question, right? How do we do this? The basic approach we use is to convert these sentences into vectors. Because we know how to deal with vectors, we already know how to see if two vectors are close to each other. We have many measures like cosine similarity, for instance, or dot product or Jaccard similarity and so on, right? And we will just stick to cosine similarity here. So cosine similarity is looking at the angle between two vectors without regard to the magnitude of the vectors themselves, right? But we will not go into detail on the similarity measures here. We'll stick to cosine similarity. But how do we convert a query or a sentence into a vector? That's the basic question, right? And there are many ways to do that. We will look at a few today, starting from the most popular technique called the bag of words, right? And these are the other techniques we will look at. We will look at word to vec, we will look at GLOW and BERT. These are all different ways of converting a sentence into a vector, and in a more fancy way, these vectors are called embeddings. So to put it differently, we want to get a sentence embedding from a sentence, right? Once we get the embedding of the sentence, we can compare if two sentences are similar to each other. Okay, before we move on now, let's get back to our notebook. So we have a Python notebook here, a Jupyter notebook here, and this is available on GitHub. You can all access this. I have some installation instructions here. You need the basic stuff like you need scikit-learn, you need NumPy and so on. If you want to do the BERT embeddings, you will need like a few more things installed. I have given the instructions of what you need to install here in this notebook. So you should be able to go ahead with that. The data set we're going to use for this task is that from MachineLearningInterview.com. So it's a toy data set, but that's okay for now because I don't have a lot of FAQs right now there, but we are going to use that. So I have written down the FAQs in a CSV file, and now it's being loaded. I have imported pandas and I'm going to just read it into a data frame here. And I renamed the columns to questions and answers for simplicity and printed them out, and this is what it is. These are the same set of questions you saw before, all right? And you can even see what is the mathematical background required to become a data scientist. Same question there, right? Okay, now we are going to see what pre-processing we need to do. So just like many machine learning tasks have pre-processing, like removing noise or filling missing values and so on, in NLP there are some common pre-processing steps that people do, right? One of the common things that people do is, here what I'm doing is, I'm removing all characters that are not alphanumeric. I'm removing something called stop words. So stop words are words like a, to, in, and so on. These are very frequently occurring words which do not give me a lot of context about the meaning of the sentence. For example, if I tell you there is a in the sentence, what does it tell you? It's not really very useful for me to know that. If I tell you there is books in the sentence or data in the sentence, that's much more insightful to me, right? So some algorithms can actually use these stop words to do a better job of prediction or embeddings or whatever, but many algorithms cannot handle these well. They just get confused because of these words, because they're just adding noise in some sense. So we are going to remove stop words for most of the algorithms except a few at the end, right? So what I've done is I've written a small function called clean sentence. What it's doing is it's actually removing, it's converting everything into a lowercase first, right? Because sometimes the representation that we get for a lowercase and uppercase might be different, and we don't want to confuse our algorithm, because we want to look at the meaning really at this point, and not so much on the case, right? And then we are going to remove all non-alphanumeric characters to because you might not be able to handle them in the algorithm. Okay, so then I have this step where I'm removing stop words. I'm using a function from GenSim. So from GenSim I'm imported preprocessing, and I am able to remove all stop words using this function, right? But I made this optional, so I have a parameter to say whether I want to remove stop words or not, because again for some algorithms I might actually want to try with stop words because it might be better. So once I write this function, I'm going to put it in a loop and call it for every single FAQ question, right? So in the data frame, I'm going over every question and saying clean sentence, right? And you can see, and I have two versions actually, with stop words true and stop words false. So it looks like this. This is what it looks like when I remove the stop words. Insights offer DS job market. Any insights you can offer about DS job market? So that's the actual question. And this is, the question without the stop words. Job hunting experience look like. What does the job hunting experience look like? That's the original question, right? So you understand the difference between removing and not removing stop words. So only the content words are present, in other words, now. Okay, let's look at the first way now. Now we come to the fun part. How do we convert these sentences to vectors, right? First, let's look at the bag of words model. So the bag of words model essentially builds a vector for each sentence, where every element of the vector talks about whether a particular word is present or not. So the first step to do bag of words is to create a dictionary of words. So as you see here, there is a dictionary of words. I've just printed a few, the first 15 words in the dictionary. And if you take a sentence like this, any insights you can offer about the data science job market. So I will create a vector whose length is the number of words in the dictionary, which is actually the number of words present in any document in the entire data set, right? So that's like total number of words. That's the length of my vector. And here, because it's a toy example, it's just like, I've taken only the first 15 to show you here, right? And then I see that, the second component is a 1, which is 1 is experience. So 1 actually is a 0 here because experience is not present in the sentence. But if you look at, let's say 3 has a 1, so 3 is job. So job is present in the sentence, so there is a 1 for job. Similarly, there is a 1 for let's say there is a 1 for market, which is 13, right? So 13 is market, and that's 1, right? So basically you have a 1 if you have that word in the sentence, or a 0 otherwise. In fact, usually if you have that word multiple times, you would have the number of times that word occurred, right? Not just 1 or 0. Okay, and this is how my representation looks like. It's like here it's a binary vector because I don't have repeated words. Now this vector could get really long when you have a big dictionary size, because dictionary size often goes to few tens of thousands if you have like a big corpus in when you're looking at NLP tasks. Even for like an FAQ question answering kind of a task, it could go to like easily thousands of words. Depending on how many FAQs you have and what is the variety of things covered in the FAQs. So it might be very inefficient to deal with these really long vectors. So one might actually use a sparse matrix representation, sparse vector representation. So here you are only actually have recorded the non-zero components of the vector with the assumption that all the other components for remaining dictionary words is 0, right? And NumPy supports this, and we are just going to use this feature of NumPy. Okay, so what we are doing here is we are going to first get a list of all the words which is present in any sentence to construct our dictionary, right? So it's just looping over all the sentences, pulling out all the words, and then I'm creating a dictionary using corpora.dictionary here, which is something you can which is a ready-made thing that you can use here, right, from Gensim. So from Gensim I've imported corpora and I've used corpora.dictionary, and then I'm just printing the key value pairs in the dictionary just to look at it here, right? And now what I'm going to do is I'm going to loop over all the sentences in the in my corpus, and I'm going to in my FAQ list, and I'm going to get the vector corresponding to each of these questions in the FAQ, right? And I can do that very easily because I have this dictionary.bow text, and that will automatically give me the embedding for a particular sentence. Okay, so and then it's just basically I'm converting the sentence to a vector using the bag of words, using the ready-made function available to me here. Okay, and then I will do the same thing even for I'm doing dictionary dot doc to bow question, right? So I need to give it like a list of words in the question, and it can actually give me the bag of words representation. So I'll just do a question dot split and give it here, right? Okay, now once I have the bag of words representation, which is a vector for both the user query and for all the questions in FAQ, what is the next thing I want to do? I want to find the closest match, right, between user query and FAQ questions. To do that, I am simply going to, in this case, because it's a toy data set, I'm going to iterate over all the possible FAQ questions and see which is closest, right? But we'll talk later about what to do if we have like a lot of questions. This might not be very efficient, right? So I'm going to just loop over all the sentence embeddings that I got using the previous function. So the previous function was giving me a list of the previous cell was giving me a list of sentence embeddings and the query user query embedding. So I'm going to loop over, I'm going to take the user query embedding, the sentence embeddings, and loop over all the question sentence embeddings and find the closest using cosine similarity here. So this cosine similarity is something that I got from sklearn metrics, right? And then I'm just doing a simple, I have a max similarity here, and I'm just looping and setting the max similarity whenever the similarity is higher than max similarity and so on, right? Standard thing to find the largest closest matching, largest in a sequence, right? Linear time algorithm for that. So once I do this, I will have in index sim, I will have the question from FAQs that is the closest match for the user query, right? So here I'm printing that question, I'm printing the original question, and I'm printing the retrieved question and answer, and here is what it looks like. So the original question that we actually, so the toy question that we wanted to look at is, so this is the user question, let's say, what does a data scientist usually do, right? So it's a very basic question. And so when if you see the output of this function, it's printing the question, what does the data scientist usually do, and it is also getting the closest retrieved question from the FAQ corpus, which is what does the job hunting experience look like. So this is not a good response, right? Do you think this is a good response? No, because you want to know what a data scientist does, not about job hunting, right? And why did this happen though? So another thing to note is that here you also have the score of each sentence in the corpus with the embedding with the query, user query, right? So this is the actual cosine similarity, just to see, like, you know, how other sentences or various sentences are comparing. But what you see is you got the wrong answer here. And why is that so? This is because the bag of words technique intrinsically is only looking at how much overlap of words is there between the two sentences, right? It's not really looking at more nuanced stuff like are they similar in meaning, right? For instance, you know, one of the things here is, how does a typical day of a data scientist look like, right? But when you actually remove the stop words and when you actually compare these two sentences, you saw that what does the job hunting experience look like got the same score as what does the typical day of a data scientist look like. That's because, number one, it does not understand that typical is same as usually, right? So it is their related words, but this bag of words algorithm does not understand that, right? Another thing is, so if you see, data scientist is something that is a very common word, and lot of answers actually have data scientists, so it might think all of them are actually matching, right? So there are many challenges when you actually look at exact match of words. So what we want to do is, we don't want to look at exact match of words, but rather we would like to look at sentences that have similar meaning, right? Sentences that are same in meaning even though they do not use the exact same words. So if you look at this, the best matching answer was, how does a typical day of a data scientist look like, is a reasonable thing for what does a data scientist usually do. And it talks about, okay, all the things that a data scientist does in, you know, a day at work. And this is a reasonable answer, right? And we want that to actually get a high score. That's what we want. Okay, so word-to-vec is a technique that attempts to address this issue by giving vector representations, by obtaining vector representations of words, so that similar sounding words are close in cosine similarity in their vector representation, right? They need not be the same word, but if they are similar in meaning, they have close cosine similarity. Or if they are words that occur together, then also they would have, like, you know, a good cosine similarity, a high cosine similarity. So the other nice thing is that it has been a very widely used model because there was access to pre-trained embeddings. So basically Google has released a set of pre-trained embeddings by training on Google News dataset, which literally had like 100 billion words, very large dataset, and it gave 300 dimensional vectors or 300 dimensional embeddings for like a few million words, literally, right? So because of that, there was something some people could readily take and use and not do a lot of training. It became a very popular model. So let's understand, you know, more about this. So the one thing we said is, similar words that occur often in the same context have vectors that are close to each other. Okay. The second interesting property it has is, suppose I take the vectors, please excuse my drawing here, I just drew it by hand. But suppose I have vectors like king, queen, man and woman. Okay. Now king and queen will be close to each other because king and queen stay in a palace. king talk to queen. So basically so many sentences, they can actually come together, right? So these are again similar vectors, but that's not the point we are trying to make here. Suppose I have the vectors for king, queen, man and woman. I can do interesting arithmetic like this. King minus man plus woman is approximately equal to the queen vector. How cool is that? Right? So this actually opens up a way to, now what I'm seeing is I can do arithmetic on a set of words to get their combined meaning in some sense, right? So if I have like a sentence, I have embeddings for individual words, and if I want to get an embedding or a vector for a sentence, I just need to add up all the vectors for the individual words in the sentence. How cool is that? That's very easy, right? And that's one of the reasons why word-to-vec became very popular. So I can get a sentence embedding by just adding up all the word embeddings in the sentence. That's one way to do it. There are more sophisticated ways to do it, but at least the simplest way to do it also gives some sort of reasonable results, as we will see. Now, how exactly are these vectors obtained? So these vectors are based on a neural network model. There are a couple of models that are popular, the CBOW and the skipgram, but the skipgram is the one that's more often used. This is the one that, Google released its word-to-vec embeddings with, Google News embeddings with. So the way this works is, note that this is not like a very deep neural network, but it's a neural network. The input layer, so suppose you have like a large corpus, let's say you have like, millions of documents you're training with, and each document has like a bunch of sentences, some text, right? So you take every word in the corpus as input, and you have some hidden layer here, and what you're trying to predict here is the words in the context. So if I take a sentence, let's say, when Harry met Sally, he said, "How are you?" Right? So when I take the word Sally, I would try to actually predict the words around it. So basically it'd be Harry met Sally, he said, right? So those are the words in the context of the word Harry. And I will try to predict basically the words in the context. What this does is, so we won't go into the details of this model, okay? But what this does is that it gives a similar, so basically finally the embedding or the vector that we get is nothing but the intermediate layer in the neural network. Whatever are the values of weights in the intermediate layer, that will be the embedding or vector that we want finally for the given word. The interesting thing here is, now if words appear in the same context, then they will actually, it can capture that relationship, and finally the semantic, the embedding of these words will be close in the result, right, in terms of cosine similarity. So you can read more about this in the Google page, but let's go back to our notebook now. The nice thing is, okay, we don't want to get lost in these details of the models. Let's see how we can use them. It's very simple to use them. That's the beauty of it, right? So I can actually use Gensim downloader, and I can actually do something like, I can just say word-to-vec model equals api.load. So can you see this? Word-to-vec model is api.load word-to-vec Google News 300. If I do that, it will automatically pull word-to-vec from the online repository, and but remember that this word-to-vec model is very huge, so it could take up a lot of your memory, and you need to be very careful while using this, right? Your application will be in like GB when you actually run this, so in memory. So it's very simple to do this, and what I'm doing here is, this is like a very large model, right? So I don't want to keep pulling this off internet every time, so I'm going to write it down to a local file, and I just have a small try catch block here, such that if it's not already there in this local file, I'm going to pull it. Otherwise, I'm going to use the local file. I've saved it to a local file, model.save. Okay, this is what I've done. Now, another similar model to word2vec is the glove model. So glove also has similar properties. For instance, words that are close to each other in semantics will have they will be close to each other in terms of cosine similarity with glove embedding as well, and it also has this nice additive property, right? But the difference is that it is trained in a different way. While word2vec was trained using neural networks, glove was trained using matrix factorization techniques on the word co-occurrence matrix. So word co-occurrence matrices, I take every pair of words and want to see how often they occur together in a context, and I have a matrix of this where the rows and columns are words, and I'm going to apply some matrix factorization techniques here. So matrix factorization was a very popular way of coming up with embeddings or vector representations before the neural word embeddings became popular, right? In fact, there are like many techniques before glove and word2vec that were used in between to create embeddings. For similarity, people used things like latent semantic analysis, latent Dirichlet allocation. So there were a lot of things that were being used. But from the time these pre-trained embeddings came up, they became very popular because you don't have to train for a particular task, and you can just take the existing embeddings and then, you know, in a given sentence you can just add them up. But mind that, you know, you need to, for example, if you use the Google News dataset embeddings for a medical task, right, which has like highly specialized vocabulary that might not appear in news, you will not get good results. You might need to retrain your embeddings for that, right? So it really depends on the task, but for a lot of tasks you can use the pre-trained embeddings. And now, apart from word2vec, we are also going to use glove here. So we called here again api.load glove to 25. What is the 25 here again? 25 is the number of dimensions of the vector. So we get a 25 dimensional vector for each word when we call this. Similarly, for word2vec, we were getting a 300 dimensional vector for each word. So while 300 might look like a large number, it's a very small number in comparison with bag of words, where the size of the vector was literally the size of the entire vocabulary you had, which could go to thousands, tens of thousands, and so on, right? So this is a small, more compact representation as well. Now let's see what happens. I've sort of put this in a small function, get word2vec for a word given the model, because note that all words might not be in the vocabulary. For example, if you take a word such as COVID, right, it will not be in the vocabulary because of the Google News dataset model, because it was trained a while back and this word was not prevalent at that time, right? But most of the common words will be there, of course. So what would I do if I get an out of vocabulary word? I just want to give like a 0 vector. So I have a simple try block where I'm actually trying to get the particular word from the model. So the model that I get from both the glove and word2vec using this API, it's just a dictionary. So I'm able to just do model word if I want to access the word, and if it is not there in the dictionary, it will give me an error, and I'm just making a vector of zeros of length 300 or 25 or whatever, right? Now how do I get a phrase embedding given the embeddings for all the words? I'm just going over every word in the sentence and I'm just doing vector addition, and I'm getting the resultant vector and returning it. That's all I'm doing to get the phrase embedding. Now there are, again, like I said, there are more sophisticated ways here, but we'll just stick to, like, you know, the bare bones simple basic way here. Okay, so now what I would do is I would call this function and I would try to get the sentence embeddings for every sentence in the question list, which is in my cleaned sentences that I got earlier. And then the user query is also being sent to get phrase embedding function, and I'm getting an embedding for it. And then retrieve and print FAQ answer is actually going over all the list of question embeddings from the FAQs and finding the closest, right? And it is going to print it. And when I see the printed results, here is what I see. The result is like this. with word2vec, what does a data scientist usually do? And what I'm seeing is something like this. How does a typical day of a data scientist look like, which is a much more relevant answer, right? So it got the right thing, the closest thing it could get, it got from the database, right? And if we actually look at the values of these various, how close each result was, we see that the best match was 0.77 in cosine similarity, while the next best is 0.64 only, right? It's quite far away, and it could actually that's good basically. If something not similar does not have a good cosine similarity, that's good, right? And other thing is, like, it could figure out that typical is similar to usually. You will see that typical and usually will have embeddings that are close to each other, right? In bag of words, this could not be figured out. Now I do the same thing with glove. Glove is a similar model. Usually glove gives similar results as word2vec. So when I do it with glove, I see that I still get the right result, right? How does a typical day of data scientist look like? And if I look at the actual values, I got, like, a very high score here, but I think the next highest score is also very close to it. So that is not great. I mean, I think this is probably because look like is there in both the sentences, but then it did figure out that typically and usually is something that it caught. So overall it was able to retrieve the right answer here, right? So so some of these could actually like might even have been a stop word. So the other things that I could do to improve this. Okay, so once we have seen how to create vectors from sentences using bag of words. Then we looked at word2vec and glove, which were doing better because they were looking at the meaning of the sentence and getting vectors that are close to each other when the semantic meaning of these words is similar, right? Now, the state of the art in this, though, is BERT Embeddings, which is a short form for bidirectional encoder representations from transformers. Now, this is the state of the art based on deep learning model. In fact, it's based on advances in NLP deep learning models over a period of last 2 years and last few years. And the advantage with BERT is it is able to capture longer range contextual dependencies. So let us take an example to understand BERT, right? Suppose I have this question. Someone types 2019 Brazil traveler to USA needs a visa. This is a question. In this question, we are talking about a traveler to USA from Brazil, right? But if I take, if I don't understand this fact that we're talking about to USA and from Brazil, even talking about US citizens can travel to Brazil without a red tape of a visa sounds relevant, right? A lot of words in this sentence are actually closely related to the user query, and one could sort of think it's relevant, right? But it's actually talking about the opposite thing of people going from US to Brazil instead of Brazil to US. But BERT is able to figure out that you're going actually to Brazil from US, from Brazil to US, and it's able to give tourism and visitor information for US consulate in Brazil, right? That's the right thing to show, right? So another example could be like this. Suppose I ask about how do I learn hill parking with no curb, uphill parking with no curb. How can I learn uphill parking with no curb, right? And then I get a response about how to do uphill parking with a curb. Now that's a very related sentence, right? So clearly there is a lot of similarity between the two sentences. But what we wanted was exact opposite. That small word no becomes very important, right? Without a curb, or that small word without, or where there is no curb, that becomes very important. And BERT is able to catch this subtle difference, Okay. Um, and again, just to get a little bit more intuition about how BERT works, so we saw that in word to vec, we were taking a particular word and trying to predict its context, and in that process, whatever is in the middle layer of our neural network became the embedding, right? If you remember. In BERT, what happens is, so you randomly remove some words from the sentence, so it's called masked learning, and then you try to predict that sentence along with those words. So it's not like you take one word and remove the exact context, but you're randomly removing some words in the sentence and trying to predict. So it sort of works in a different way. Overall, you need to understand that it captures long-term dependencies better and is able to get, understand the more subtle meaning of the sentence by getting these deeper contextual dependencies. So one more thing. So if you look at a word like, let's say, go. Go is a verb, right? Please go to the market and get me some eggs. But go is also a noun, it's a game. There's a game called Go. Now both these will have the same embedding if I take word to vec, right? But they're completely different things, and the meaning completely changes based on the context. I should be able to say whether it's the verb go or the game go. So in BERT, one thing that happens is you get different embeddings for these two different contexts, right? These two different use cases, the same word go will have two different embeddings. And that's because we are not taking individual word embeddings and adding them up, but so in BERT, usually you get an embedding of the whole sentence so that these nuances are preserved, right? So if you remember in word to vec, what did we do? We got the vectors for each word and added them up to get sentence vector, right? In BERT, we don't want to do that. In BERT, if there's a way to get give a sentence to it and directly get a vector representation of the whole sentence, that's better for me. So in order to do that, if we want to train our own BERT model, it's pretty hard, but it's not hard, but it's beyond the scope of this tutorial. So what I've done is, there is a small package to run a BERT server in the background that someone has written here that I'm going to use. I've given a reference here. So it's PyPy BERT embedding. If you take, it will help you create a BERT server in the background, and you can actually when the BERT client actually calls, so I have a BERT client here, and it's calling with two phrases, who's the best ML scientist, and another phrase with just one word. I can actually get the embedding for both these words, right? And so this is again capturing the context better, because I'm giving the entire sentence and getting the embedding for the entire sentence instead of doing word level and adding up. So another point here is, because BERT is able to use these subtle differences, I don't want to remove stop words in many cases with BERT, because take a simple example. Suppose someone asks me, what are the things I do not need to prepare for data science interview? And again, I don't want to show what are the things I need to prepare for a data science interview, right? So it's like completely different, and I don't want to remove not because it's a stop word, right? So here I'm going to use the stop words instead of remove them. So I am calling, so what we are doing here is, we are saying stop words false, stop word removal false, and we are again getting, we are cleaning the user query and getting an embedding. And similarly, we are getting, we are cleaning the user query and all the FAQ questions without stop word removal this time, and then getting the embedding for all the FAQ questions using BERT, and then getting the embedding for the user query using BERT. And then we call the same question, retrieve and print FAQ answer. It is going in a loop and checking which is the closest in terms of cosine similarity. And if you see, it again gets the right answer here. What does a data scientist usually do? It's getting the right answer, right? And again, if you see how close the next best answer is, it's not very, Yeah, we can look at that later, right? So, okay, now all these things work for us, right? Word2Vec worked, glove worked, BERT worked. We had 3 different things that all worked. Now, let's look at a more complex sentence, right? Another example. Is it required to have background in algorithms and complexity for data scientist roles? Right? Again, this is a very common question. Mostly people with a non-CS background might ask this because they don't have usually a course in algorithms data structures, right? So now you have, again, what I'm going to do is I'm going to clean this sentence first with stop word removal for word2vec and glove, and then I'm going to do without stop word removal for BERT, and I'm going to see the result from I'm going to see the result from word2vec, and I'm going to see the result from BERT. And in this case, what I see is with word2vec, the question was required background algorithms, complexity, data scientist roles. These were the content words, and I got what is the mathematical background required to be a data scientist. So it sort of thought algorithms and mathematical maybe is sort of similar, but yeah, so this is what it got. It's probably not like, it's not the right answer clearly, but it's hard for the computer to figure that out, as we can see, right? So if you look at BERT, is it required to have background in algorithms and complexity for data science roles? It got, is preparation of algorithms and data structures needed for data science interview? Right? So again, that is the closest answer here. It's a reasonable answer to get from the FAQ, right? Do I need to prepare algorithms and data structures for data science interview? Is something that is reasonable to prepare in this case. Reasonable to show in this case, right? So this is the end of the code along part of it, but I would like to discuss a few more things in this context, right? So if you want to actually implement this kind of an application in real world, right? So now you did like a toy data set where things were a little easier for you, but okay, if you want to do this on, let's say, a very large data set, so the simple linear search of going over each answer and seeing which is closest might not scale very well for you, right? So note that this need not, so what we learned today is semantic similarity techniques, right? So how to see if 2 sentences are similar. That's the crux of what we learned today. We used it for automatic question answering from FAQs. We can use it in many places, right? For example, you can use it in product recommendation. If the user types a query in an e-commerce website, you can look at all the product titles and figure out which is the closest title to retrieve using this technique, because it's again sentence similarity, right? But in that case, you will actually have like maybe millions of products available, and if you just keep going over every product in each question, right, so it becomes very cumbersome for you. So usually there are techniques that people use. For instance, one popular technique for a long time has been using some kind of space partitioning techniques like KD trees, a hierarchical technique. This is available easily in SciPy. You can actually just use it from SciPy. Another technique that is commonly used is locality sensitive hashing, which is an approximation technique. So you can go and look these up. We are not going to do these going to write the code for these, but these are popularly used, okay? And this is only if you want to make sense if you want to implement this really somewhere. The other thing is, when you're actually thinking of this as an application, let's look at the FAQ matching as an application. You need to think of a few other aspects. How do I evaluate if I have done a good job of it? So if you are learning a machine learning model, typically you will measure something. If it's classification, you'll do precision and recall. If it's regression, some kind of RMSE or whatever, right? You'll come up with a measure. Now we need an evaluation metric here as well for this application of FAQ matching, right? So intuitively, what do we want to do here? We can say, okay, how many times did we actually retrieve a relevant answer, right? That could be the simplest evaluation metric. We did not do that in the notebook because our emphasis was just to understand ways of semantic similarity, but this is not hard to do. So for this though, you need label data. So what I need is a bunch of user queries, and then the best response from the FAQ that is relevant, and if it's not relevant, I need to know that nothing is there that's relevant. and someone needs to create the data set. I need labeled data, right? And then I can actually measure how many times did I retrieve something relevant. And very often you don't retrieve just one result. For example, if you're doing that kind of a recommendation kind of a project, instead of, let's say, FAQ matching, you might actually get, like, the top 5 most relevant products. Even the FAQs, you might get, like, the top 3 relevant FAQs. So for example, in a lot of assisted chatbots, right, you would have a scenario where a customer service representative gets a question, and then the 3 closest FAQ matching questions are shown to the representative. If any of them makes sense, they can choose that. Otherwise, they type an answer. That still saves a lot of time, right? So it's like a semi-automated approach. And for that, again, you're getting, like, 3 answers usually, and you want at least one of them to be correct. So another metric would be how many times is the most relevant answer in the top 3 or top 5 or something, right? So there are many other ways to come up with the evaluation metric, and that is something that you can look up as well if you are going to take up a project like this. Now, the last thing I want to mention is, in a realistic situation, if I go to a website and type what is the impact of COVID on job market, and someone shows me, oh, in 2016 job market was booming, it's a very not relevant for me, right? So I will be very unhappy about the answer that I see. So in that case, COVID is a new word. Suppose in this case, it's actually there in the FAQs, I think. Let's quickly look at the FAQs here. So yeah, so what's the impact of COVID on data science hiring? It's here, but we might not actually find it in many FAQs if they've not updated it. So I don't want an irrelevant answer. I just wanted to say, okay, I don't know, I don't have the answer to this, or someone should actually come and type the answer maybe, or I should get a manual intervention there. So I need a notion of confidence. I will always get something that is the closest, right? So if I look at the user query and list of FAQ questions, always there will be one that is closer than others, but it does not mean it is always relevant. So I need to make sure that the closest answer is relevant. And so basically there are many ways to do this. I need some notion of confidence, right? You need to figure out, like, how to filter out answers that are not at all relevant. And this could be, for example, if you look at these values, right, I could say the highest value here is 0.89 is preparation of algorithms and data structures needed for a data science interview. I can actually say if it is greater than 0.8, only then I'm going to show it the result, because if it's less than 0.8, it means I'm not confident. Or I could say if the next closest answer is quite has a score that's quite different from this answer, if I know that only one answer is supposed to be true and others are wrong, then I can do something like that. I mean, it depends, right? But I need to come up with some notion of how confident I am, right? So with that, and of course, in a real application, there'll be many other aspects that you need to take care of when you are implementing it. But for now, let's stop at this, right? I will take a couple of questions now. So yeah, one of the questions is, what are some of the other techniques of semantic similarity? Okay, so like I mentioned, I think in the talk, there are many ways to actually do semantic similarity. The most commonly used one, at least for a long time, was bag of words. That was one of the simplest techniques that you can use. And then there are again some of the standard things that were used are otherwise TF-IDF. So TF-IDF is another way where you give more weightage to words that are rarer and less weightage to words that are common automatically. So it's called term frequency inverse document frequency, where frequently occurring terms get less weightage and not frequently occurring terms get more weightage, right? So TF-IDF you can look up and you'll find that. Then of course there's something called latent directional allocation that also for a long time that became popular and people started trying to use that as features for various stars, right? And again, there are like many algorithms between word2vec and BERT also, which were actually trying to get the embedding of the entire sentence, taking into account the context. Then they were also between word2vec and BERT, they were like Elmo based embeddings and then universal encoder. Like there are a whole bunch of them, right? And it's, you can actually go and look it up and just type it in Google, what are various types of word embeddings, and you'll find all of these, right? So yeah, but I think what we saw today are sort of very representative, except for TF-IDF, which is also important. What we saw today are like the most popularly used ones, pretty much, like word2vec, BERT, right? These are the most popularly used ones. Right now BERT is used, and like before this maybe Elmo was popular and so on. Okay. Can I how do I get started with NLP? Okay, so to get started with NLP, there are many resources available. Honestly, it's like a very broad question. I personally started by taking a Coursera course on NLP, and I think Coursera courses are great, but you need to be self motivated in order to do all the assignments actually, and sometimes people are not self motivated. So there are many structured course programs also to actually go and learn. Online courses, NLP. I would also say that, you know, there are many tutorials on Medium towards data science and all that, and analytics vidya. A lot of sites actually have very good tutorials. What I would say is take a problem in Kaggle, simple problem, and just try to solve it, looking what code is there, and I think that's a good way to get started. If you want to do it in a more structured way, I would say like try an online course. Books are also a good way, but personally, yeah, it really depends on, you know, which medium appeals to a person. Okay, it was awesome doing this session, and these are available on GitHub. So basically this code is available on GitHub, and I'll be happy to share that with you. You can actually follow the entire tutorial along with the code, like in a code along fashion. Okay, awesome. Have a great time, folks.